Ladies and gentlemen, welcome back to Functional Analysis. So we're currently discussing the, powerful Hilbert-Schmidt theorem as displayed here on the slide. Let's quickly read out the statement again. So if you have a compact operator on a Hilbert space, which is positive, and the Hilbert space is separable, remember positivity implicitly means that the operator is self-adjoint. And then, as it turns out, there is an orthonormal basis for the Hilbert space consisting of eigenvectors with underlying eigenvalues that can only accumulate at zero. That part we already know from Ries-Schauder. We don't know yet that eigenvalues exist and associated eigenvectors, but this is precisely the statement of this theorem, and there's plenty of them, so many that you have an orthonormal basis of your vector space. More to the point, there exists two countable orthonormal sets, the x sub n's and the x sub m primes. Put together, they form your orthonormal basis, and the x sub n's, those are the eigenvectors of T with corresponding positive eigenvalues lambda n. You can order them in this non-increasing fashion. Again, if there should be infinitely many, then they can only accumulate at zero. The xm primes, on the other hand, those are eigenvectors with eigenvalue 0. All right? This is the theorem that will take the longest to prove in this module. And what have we done so far? Well, we have this little proposition here out front, which is an exercise in, Cauchy-Schwarz inequality, and using the Ries representation theorem. And then you get part 1 and part 2 you get for free, because we know that compact operators map weakly convergent sequences to norm convergent sequences. All right, now, the beauty of this theorem is that it gives you an algorithm how you can compute eigenvalues and eigenvectors without having a characteristic polynomial, so without having what you are very used to from linear algebra. All right, so this is a variational principle that is here at work, an optimization principle, if you want to call it that way. And it goes as follows. So you start with this closed unit ball, then you define a map on it that maps into the non-negative real half-line. This is because of positivity of T. Then you argue that its image has to be compact, and that you do by, the boundedness you get for free, and for closedness you have to exploit some heavy theorems, I would say, but all of which we have prepared. Particularly, it requires that if you have bounded sequences in reflexive Banach spaces, then they have weakly convergent subsequences. So that's a big one, but we prepared this a while ago. Then once you have the weakly convergent thing, you lift it to norm convergence under the compact map, and using the proposition, the one that I just went over again, you conclude that that space W up there, which is the image of the closed unit ball under the map F up here, is actually both bounded and closed. Hence it is compact because it's a subset of the real line. Good. Then, since you're dealing here with a continuous function, again, remember this f here is not linear, that you can easily verify, but it is continuous because T is linear, hence continuous, and the inner product is continuous in both entries. So this is nevertheless a continuous map, and its image is compact. So then metric space theory tells me there exists extreme values, right? And here the one that I'm after is the supremum. Right, so there exists a point x1 in my closed unit ball that optimizes, this function f. That's the only thing which is written there. And then using the exercise, that's an important input, which I didn't show here in the video because it is an exercise problem. That thing is actually equal to the operator norm of T. All right. Now, once we have this point x1, now we will show that that guy is an eigenvector, and we will compute the corresponding eigenvalue. How to do this? Well, here's a little bit information already written down. We did this last time. First, there's a small argument why you can assume that x1 is a unit vector, has unit length. And now the argument to show that this guy is an eigenvector, and the corresponding eigenvalue is actually lambda 1. Note, by the way, once I achieve showing this has a curious consequence to it, because so far what we know is whenever you have a bounded operator on a Banach space, then the spectrum is sitting inside a large enough disk, right? Well, disk if you over the complex number field, interval if you are on the real line. And the radius of that disk or interval is precisely the operator norm. So now what this part says, that we don't know yet if that yellow stuff there is optimal, right? When we prove this, we use the Neumann series expansion, but we don't know from that argument yet if, you know, there's actually an eigenvalue whose complex modulus or absolute value is equal to the operator norm, right? But here that part precisely says there is one, right? So that's a neat byproduct here. Good. Now how to show that this is really true, what I'm saying here, aka that x1 is an eigenvector with eigenvalue lambda1, which is the operator norm. Well, there's a little bit of trickery involved. So we define this family of vectors. They're indexed by a continuous variable t arbitrary real number. So these are unit vectors. They have unit length, and the y here, that is a vector orthogonal to x1. All right, good. So now what happens? Well, there's a little computation here. It's a sort of Pythagorean identity here that just you get from the orthogonality of y to x1, and that line there, that's where I stopped last time. All right, so now what you have to do is you have to take your formula for z of t, substitute it in there, and then exploit all the properties of the inner product and, well, get something. So what are you going to get? Well, there will be denominator, because the same denominator, that norm, appears in both entries, so the denominator will be squared. This is a scalar I can pull out, so you will have this in the denominator. And then what you have on top, now yeah, okay, so there's some algebra now that you have to carry out, but there's no surprises there coming along. I will just write out the result. You can check for yourself. Okay, there will be tx1 acting on x1 in the inner product, and 2t, the real part of the inner product, tx1 acting on y, and then the last part will be a t squared ty comma y. That's what you get. All right, however, remember that vector, that family of vectors z sub t, they all have unit length, so they are in the closed unit ball, right? Yeah, but that means in turn that then this guy has to be less than or equal to this guy, because x1, remember this was the supremum. Did I call this capital X? Yep, I called it X. Tx comma x, right? And so this here, of course, has to be less than or equal than that supremum, right? That's clear. Yeah, but now if you use the formula that you have up here and replace the left-hand side, then you will have, of course, the tx1 appearing here as well, and you have it here in your upper bound as well, all right? Then you take that inequality, you divide out, not divide out, you cancel out the these two terms, you simplify, and then you will realize, since this has to hold here for all t in R, this can only happen when this linear term here, linear in t, so that can take any sign you want. You can make it as large negative as you like, because t is a free parameter ranging on the entire real line. This here is always going to be non-negative, right? Because you have a positive operator, this is going to be non-negative, and you have a non-negative number t squared in front of this, right? But this guy here, you can make the one before with the linear power in t, you can make as negative as you like. And then you will figure out, when you write down this inequality here, that this here holds only true for all t if that linear term is equal to 0. Okay? So I'll leave that to you to check. That's not hard. So we must have that linear term is gone, and that happens precisely when the real part txy is equal to 0. Okay? So that's half of it. But if we go back to the beginning, so choosing that vector y orthogonal to x1, and then also, or likewise, of course I can multiply 0 with any scalar, then it will still be 0, so I multiply it by negative imaginary unit. So you have this. And now what you can do is you can repeat that little computation with the family that I had here. So here my family was z of t, which was x1 plus ty. Now what you do is you just do it plus ity. So you replace everywhere where you see y, you replace it by imaginary unit times y. And you do the same thing again. This here is not going to change. And what will change here is instead of a real part, you will have an imaginary part. That's the only thing that changes, right? Then bringing the same argument again, because the x1 guy, that's the optimizer. This can only hold true if the imaginary part of tx, y in a product is equal to 0. Okay, let's write this down. And repeating the last computation. The last computation with, well, as I said it in words, iy instead of y. We also deduce imaginary part of tx1y, tx1, y is equal to 0. So together, real and imaginary part are equal to 0, so that means y is orthogonal to tx1, right? It is by choice of y was orthogonal to x1. Now we showed it's orthogonal to tx1. So what do we have? Tx1 is in the orthogonal complement of, okay, I will write something down, then I will erase it again. So yeah, it is orthogonal to this one set here, or all linear combinations. I could write the span of y, it's true. Yeah, but y is orthogonal to x1. So if you want to write it like this, then you have two orthogonal complements. Yeah, but this we know from the exercise. The orthogonal complement of the orthogonal complement of a subspace is the closed subspace. Here that x1 is not a subspace, but you can do the similar exercise. That turns out to be the span of x1. Okay, maybe let's write this here. So if you have a yeah, so if you have a subspace S in a product space V, and you take the orthogonal complement of the orthogonal complement, you get the closure. This was an exercise. Now if this S is not a subspace but a subset, I don't know, T, and you do the same thing, which you can because the orthogonal complement is defined for any subset, not necessarily subspace, then you get here this guy here, okay? So span of T and then closure thereof. Now up here I don't need a closure because this is just a one element span, right? So it's just all linear combinations, okay? So but what is the span of x1? Well, I just said it, all linear combinations, alpha f, and that's precisely what the eigen, this is a mistake, this is in there, and this here being in here is precisely the eigenvalue eigenvector equation. Tx1 is a multiple of x1, that's precisely eigenvalue eigenvector equation. So this means Tx1 is equal to alpha x1, and since Tx1 x1 you already know is equal to the operator norm, you now substitute the eigenvalue eigenvector equation into that inner product, you simplify, you will find out that alpha is actually the operator norm of T. So we conclude Tx1, call it lambda 1, x1 with lambda 1 being the operator norm of T. Okay? Good, so that's how you can pull out the first eigenvalue eigenvector pair. And this is a construction that I would encourage you maybe do it for a 2x2 matrix. There it's just a calculus optimization problem. You have to use Lagrange multipliers and optimize this expression. So you go in, say, in R2, you equip it with a dot product, take your favorite Hermitian matrix, look at this TXX business, and then optimize it over the closed unit ball. It will spit out the eigenvalue, and that thing is actually equal to the matrix norm. All right. Good. So now let's move ahead. Next, so how do we get more eigenvalues, eigenvectors out of this? Well, now sort of an iterative inductive procedure starts. So I look at H1, which is the orthogonal complement of span of x1. All right, so just to remind you, these are all vectors in my Hilbert space that are orthogonal to x1. All right, then next define this and note. Now I would like to restrict, of course, my operator to that space, but it's not so clear yet if that actually then will be an operator after the restriction or if it will be a linear transformation. Hopefully it's an operator, so let's check that it is true. And note that for any x in H1, so let's do a little computation, tx, x1, well, it's the self-adjoint guy, so you can move it over there unchanged, x, t, x1. Now tx1 is lambda 1 x1, so x, lambda 1 x1. Lambda 1 is real because you're dealing here with self-adjoint operators, so you can move it out unchanged. It goes here, so you have lambda 1 and then x, x1. Yeah, but x is in H1 and those are all vectors for which this last inner product is equal to 0. So this guy is equal to 0, right? So this means in turn, so the image of H1 under the map T is again contained in H1 because that inner product is equal to 0, right? Test, we have that for the restriction, call it T1, so this is T restricted to H1. We have that for T1, this is really a compact operator on H1, right? So I have to check that this restriction is really an operator on that space. So it maps the space into itself, right? And that is achieved here by this little computation. And now since T was compact on the whole space, in particular if I restrict it to this H1, it's still going to be compact. All right. Moreover, it is also positive. That requires no explanation because positivity is defined by having those inner products being non-negative for all vectors in the space. So you just restrict your vectors to H1 and then you still have it. So moreover, T1 is also positive. So as above, and now we repeat our optimization, the variational approach just for T1. So as above, I can find next vector. There exists x2 in H1 of unit length and lambda 2 non-negative such that, well, tx2, yeah, but x2 is in H1, so there it's just a restriction, so t1 x2, which is lambda 2 x2, right? Moreover, lambda 2 is actually the operator norm of the restriction, and that of course cannot exceed the initial operator norm, which was lambda 1, right? So and that's how you get the second eigenvalue eigenvector pair out, and you can see now these eigenvalues, they are ordered in a non-increasing fashion, right? Okay, and then you now keep the machinery running. So proceeding inductively, we find vectors x1 up to xn of unit length, so that these are all eigenvectors of T. The eigenvalues are the operator norms of those consecutive restrictions, and they are ordered in this fashion, lambda j minus 1, and then some more properties about the eigenvectors. You could see this here. So the next one, so here was the 0th step, I generated x1, and then the next one was x2. x2 was in H1, right? So that in particular means x2 and x1 are orthogonal, and that property persists all the way. So the new ones that you generate, they're always orthogonal to the previous one. So what you're actually getting here is an orthonormal set of eigenvectors. Okay, that's what I'm gonna write down now. then hj, which is x in h. These are all vectors that are orthogonal to the previous ones, so that xj plus 1 is in there. That's exactly what I just said. So in each step you generate a new vector, an eigenvector, which is orthogonal to the previous ones, and that's precisely what's written here if you read how hj is defined. Okay, h sub j is defined. Okay, the eigenvector eigenvalue equation is also good to have on paper. So txj plus 1 is equal to tjxj, and here's your lambda j. Okay, good. Where, let's write it also out. Tj is just a restriction of T to the hjth space. Is compact and positive. Okay, excellent. Now by construction, that I already said in words, you're generating here an orthonormal set of eigenvectors. So xn, n1 infinity is an orthonormal set of eigenvectors. All these eigenvectors, they are ordered downward. So lambda 1 is the biggest, and lambda 2. They could be equal to one another. I'm not making here any statement about multiplicities, as you know that from linear algebra. Some of these lambda j's, they could be equal to one another. And lambda j plus 1 is equal to Tj, which is the operator norm of the restriction of T to Hj. Okay, now moving ahead, since we have an orthonormal set of vectors, Bessel's inequality guarantees that argument we have applied a few times already. If you have an orthonormal set, then if you look at these vectors in there, send n to infinity, that will converge weakly to 0. This is Bessel's inequality. And so by the property that compact operators map weakly convergent sequences to norm convergent sequences, you actually have lambda j, which is lambda j xj, because xj has length 1, and lambda j's, they are positive, because you're dealing with, or non-negative, that's more accurate, because you're dealing with this positive operator. Then this is equal to this, but since xj, as j goes to infinity, goes to 0 weakly, the image sequence txj here in norm will go to 0 as j tends to infinity. Okay, so we also have this property that the lambda j's, they can only accumulate at 0. All right, so now having this orthonormal set, now we have to argue how we can generate a orthonormal basis for the Hilbert space out of it. Well, here's the trick. So look at those hj's and let them intersect. All right, then the intersection of any vector space, this can be countable, uncountable, is always going to be a new vector space. And also here, since we're dealing with these orthogonal complements, the same applies for these guys. Okay, so look at H infinity, that's definitely going to be a vector space, no question there. It's a subspace of the original H, because each Hj is a subspace of the original H. All right. Recall that our Hj's are nested. So the next one is sitting in the previous one. This is, you can see by the definition up there. Here, this one. So that one Hj, there you have all vectors that are orthogonal to j vectors. In the next instance, you got all vectors that are orthogonal to the first j ones plus one more, right? So that's clearly going to be a subspace of the previous one of the Hj, all right? And obtain in turn that if you restrict T to H infinity, then that guy is going to be less than or equal to all the eigenvalues for all j in n, right? This is simply because of the previous property that we had up there, right? Here, for instance, this guy. Okay, so in turn, because when j goes to infinity, the lambda j's level off to 0, hence the operator norm there is 0, so that means t restricted to h infinity is the 0 operator. That is to say that h infinity is surely in the kernel of t, right? That's the best thing that you can pull out of that. Okay, I will stop here. So we're not there yet. We still have to argue how you can now cook up that orthonormal basis. We haven't used the separability yet, but this will come now. This will come. Once we build in the separability, then it's not much further down the road until we get to the end result. That is to say that we complete the proof of the Hilbert-Schmidt theorem. Good. Once then this is done, then comes the spectral theorem, or which I call here the spectral decomposition theorem. And as we will see, this will be more or less a corollary to the Hilbert-Schmidt theorem. I will see you soon.